So this was a really important engagement process because through this process, it became really clear that what I thought was valuable and what I was delivering to farmers, even though it met all of my expectations and aspirations, didn't actually seem to be useful to them. Clearly, I had imagined a very different value proposition to the farmers. So,
just a minute. Please share your screen. Because your
you can't see my screen.
Yeah, your slides, they are not visible.
Interesting.
Yeah, please.
Stop sharing. Let me try again. I can't share screen anymore for some reason.
If there is permission for you have to click on the share screen. Then
it's blanked out for me now. I could share screen before, but not anymore.
it will ask permission, then I have allow from here.
Yeah. What if I turn off the camera? Yeah, it's blanked out. What? What I can do is I can share my slides afterwards. It would be better to be able to show you, but if we can't share them now, I'll just continue, and maybe I'll put them in the chat after.
Okay, continue with your presentation, please.
Sure. All right. So basically, I had made these almost models for farmers, and they didn't see them as useful. And I'm not sure if any of you have had an opportunity to go out into the field and talk to farmers or end users about nanotechnology, but I'm pretty sure that you're going to get a similar reaction to what I got talking to them about soil moisture remote sensing. So you can start with buzzwords like nanosensors and describe how the components fit together, or you can try and describe what the signal of your data looks like when you plot it on a graph. But I would encourage you instead to prepare to answer questions like, how does that work? Do you know that it works? What does it tell you? If you go into more detail, you're pretty likely to get a confused or doubtful expression from the farmers. So instead, perhaps preparing something, instead of using lots of technical language, instead preparing something with lots of pictures is really helpful. And get ready to answer questions like, is it going to break if my tractor drives over it? Or can I leave it out in the rain? So you might be, in summary, when you're going about applying your research and technology in the real world or with your end users, I encourage you to engage with them as early as possible, to listen to what they think their problems are. So instead of imposing your opinions on them about what you think their problems are, listen to them and ask them what their problems are. Consider and implement their feedback, and then engage again. And build end-to-end products. You don't want to leave an end user with a half-finished solution. You really don't want to half-fix their problem. That's of absolutely no value to them. Make sure you build products which are useful from end to end. So basically, the definition of collaboration, in summary, is the act of working together with other people or organizations to create or achieve something. The key point here being working together. So, it would be really good if you could see these slides, but what I ended up moisture remote sensing model after engagement with these farmers is a time series data product. So basically it showed monthly maps of soil moisture and it answered their question of, can you tell me where I will get bogged on my farm? So basically by creating monthly maps of soil moisture, we could do change detection and it was really obvious to them. We could make monthly maps of the risk of getting bogged across their property. And they said, that's great, can you post them to me? So instead of having a highly technical, interactive digital dashboard for this data, they wanted someone to print out these maps and post it to them. So what about nanotechnologies? It's really, like, soil moisture remote sensing is really cool, but you also need data to be able to build remote sensing technologies. And nanotechnologies, I think, offer a really unprecedented new opportunity to build some great technologies. Again, you should have a look at these pictures afterwards. There's 4 different types of sensors shown here. And what I'm proposing is if nanosensors, because they're so small, because they can be customized in so many ways, what if they were made to be more familiar and more practical? So for example, what if you made a sensor which could, so you might have farmers ask you things about about sensors and things like, can I drive over them with my tractor? Will they break? Or how do you move them around the paddock? What if I want to put it somewhere else? So what I've got shown here is a clear board with a sensor in it. So instead of having a sensor that is like stuck in the ground somewhere that can't be moved, maybe you just have a nanosensor in a ball that could be thrown around the paddock, or it could be just dropped somewhere. If it was driven over or there was a cow stood on it or something, it wouldn't be a problem. It would still be collecting and transmitting data. Similarly, what if you had a sensor on a stand that was flexible? So this way, if a tractor drove over it or something else, it would just bend out of the way and the farmer would continue on their way. So there's really a great opportunity, I think, to with the optimizations that nanosensors bring to data collection technologies. I think there's really a great opportunity to reimagine what sensors and field equipment looks like. And so with this opportunity, you might be wondering what happens when you engage with end users and, like, is it actually worth it and why would you bother? There's quite a big amount of research actually on why you should bother. And so some of the benefits of data and product sharing are things like it improves the impact of your science. It allows you to combine data sets from lots of different users and sources. That gives you increased statistical power to run bigger models on. You're more effectively using equipment and funding that you have. Basically, there's benefits for everyone. So some of the benefits for you might be new collaborations and recognition within your career. You might get more citations because you have more exposure. For the public, there's opportunities for citizen science and involvement in scientific research and engineering, which usually the public would be excluded from. And there's also benefits for the whole research community. So basically, in this case, the whole is greater than the sum of parts when we collaborate. So by collaborating with end users, you can have a much higher impact than you would otherwise. There's already a lot of literature on this topic, so if you're wondering how to do engagement with end users, go and look for some examples. Don't try and reinvent the wheel. So I've got a resource here which shows how collaboration between scientists and farmers in Africa greatly improved the productivity of agricultural practices there. So basically, in conclusion, the decreased size and power consumption of nanosensors present lots of new opportunities for innovative sensors and sensor mount designs. Improved communication capabilities in new technology allow more remote sensors and unwired sensors. It's actually, however, impossible to know what is actually useful for end users, though, or practical to use in the field without working directly with these end users during the ideation, optimization, and testing phases. So, any questions?
Thank you, madam, for the presentation. I think it would have been much better if you had given the presentation along with the slides, because many times, some question comes while the audience, they will see the slides and then the question comes instantaneously. But anyway, you were facing problem of sharing the slides. So I request all my audience to please join me in thanking this participant to do the presentation. The floor is open for one or two quick questions, please. No question? So generally I say that if there is no question, that means everything is clear or nothing is clear. Okay. So I hope that this is not the case, second case. So, madam, since you are not here, otherwise we would have presented you this, token of appreciation. So I think the organizer, they will send you by email. Okay. So once again, thank you for your presentation. Wish you all the best.
Pleasure. Thank you.
Thank you very much. So now I will invite the next speaker, Professor P.K. Singh from Chanda University. He is the head of the department Solar Cell and Department of Renewable Energy. So the talk, we will be talking about the tailor-made material for dye-synthesized solar cell and the super capacitors. आपने 15 कहा सर 13 नहीं आप 17 कर सकते हैं I will give you another 2 minutes as bonus.
So I think good afternoon from my own side. Let me thank first of all the conference organizer. I think Professor Eshen Singh and Professor Anurag, Dr. Anurag, who invited me here to present some of my works. So my talk is related with industrial application of polymer electrolytes. I am coming from a private university, let us say it's a state university which is located nearby our capital Delhi. It's known as Sarda University. So it's private university, and I'm coming here with my most of PhD student who is from abroad, who is from Nigeria. So some of my senior, my PhD senior, Professor Hasmi, and other juniors, they are attending here. So I am presenting something, work which I have carried out under the closed, you can say, guidance with my PhD supervisor, Professor Suresh Chandra. So our backbone is related with solid state ionics material. It's widely classified into various classes, but particularly since chairperson already given me 15 minutes, I am going to try to find out, finish, and comprise each and everything within 15 minutes. So these are my research credentials. Anybody can see through that one. Basically, in Sarda University, I am heading two departments, physics and environmental science. So in physics department, totally we have 21 faculty members, along with in environmental science there are 9 faculty. So my family, let us say, it's a big family, and I am heading those family. Particularly here I am going to present something work which is dedicated particularly on my laboratory point of view. So my area of work is related with polymer electrolytes, and in our own laboratory that is known as Center for Solar Cell and Renewable Energy, we are basically focused on nanomaterials, polymer electrolyte material, carbon electrodes because we are working in supercapacitor area, and then nanocomposites. We have good characterization tools, which I am going to see you in coming slides. And basically, these are industrial application of this polymer electrolyte. But since I cannot cover whole things, so my work is basically related with solar cells, particularly in dye-sensitized solar cell and supercapacitor. So, as I have already told you, we have a very good laboratory that is known as Center for Solar Cell and Renewable Energy, which headed under my supervision. And this, you can say, Center for Solar Cell and Renewable Energy, I mentioned as a HOD, and then members are my colleagues. So we are collecting all over faculty within Sarda boundary, and they are working closely, those who are related to material science. And then this core team is dedicated to my PhD scholars, which is not PhD scholar with this center, maybe within Sarda University. Some of them are present here, maybe from electronics and other departments. And these students are going to maintain their UG and PG students. So this is looking like a carbon cycle. At least I can say that I am able to manage all those faculty members, my colleagues, and as well as my students. So these are overall overview of physics department only. We have already produced near 26 PhD scholars, and these are some research scholars which is still continue with physics department faculty members. This slide is particularly related to my own credentials. So till today, I have, you can say, publication point of view, my publication is more than 300. And basically, as I have already told you, I am working in supercapacitor using polymer electrolytes, and then same electrolyte we are using for dye-sensitized solar cell, where electrolyte is 1%. These are some major equipment which is already situated in my own laboratory, and it's free for students. So particularly came here, one of other motivation of my present work is that any student can contact us anytime. We are free. We are, you can say, free hand for any type of collaboration related to our own area. So here, particularly for this presentation, I have already prepared a good slides, which is going to cover, I think, not more than 10 minutes or two. And it's a collaboration with my Polish guy, his name is Professor Tagore. And this is my, you can say, master student. Now she got PhD with this professor. So ultimately, I have found a new collaborator from, you can say, Poland. So some of the work which I am going to present here, it's already published in a very good journal. And I have already going to maybe remove this slide because this is related with our, we can say, our old tree. So we are working, we means solid state family, our supervisor, like Professor Suresh Chandra, he wrote a very good book. Anybody who want to enter in this area, he or she must read this particular book. And this polymer electrolyte, I am coming to solid electrolytes, the solid state ions, it's a different class. My work is particularly related to polymer electrolyte. And these polymer electrolytes have various applications in electrochemical devices. Particularly, I am going to cover with my own laboratory only with these two devices, dye-sensitized solar cell and supercapacitor. The dye-sensitized solar cell, something in solar cell. When I was doing my PhD work, that time in conclusion portion of any paper, I have simply mentioned that these polymer electrolytes are very good conductivity, may be used in dye-sensitized solar cell application. But I am lucky person because I got a postdoctoral fellowship with South Korea under Professor Uri, where I learned something related to dye-sensitized solar cell. And then I have used this polymer electrolyte to make this dye-sensitized solar cell. Now, the one basic problem who are working, most of people who are working in this polymer electrolyte, this one is particularly one very low ionic conductivity of these polymers or polymer electrolytes. So there are several approaches, and particularly you can say after return back from South Korea, when I joined Sarda University in 2009, still continuing in Sarda University, we have learned something about the new kinds of doping that is known as ionic liquid. So I'm not going to tell something about many things related to ionic liquid. So ionic liquid is a very good, you can say, plasticizer along with ionic source. So I have purchased too many ionic liquids and directly or with salt I am doping in this polymer electrolyte. And what I found that one most barrier, which is low ionic conductivity, get removed. So we got a very good conductivity, and particularly for these kind of things, I am giving you only one example because I have published several papers in coming year. I have already published, so anybody can go through these papers. Now I am just giving you one example of one polymer electrolyte, and then I am going to finally conclude this overall talk. So polymer electrolyte, let us say I am giving you one example of this polymer electrolyte. This is one polymer electrolyte. This is one polymer, polyethylene oxide, which is our backbone. Because we starting from PhD work, we only mostly heard about this polyethylene oxide. So when I was working for my PhD degree, that time my senior told me that this polymer electrolyte, this PEO, is not making friendship with too many salts or too many dopates. So that time I learned that if you go to ionic salt, means ionic salts will be cation anion, conductivity is going to increase. But these kind of dopates, means ionic liquid, which I have already told you, I got something glimpse about this ionic liquid when I was doing my postdoctoral fellowship in South Korea, and we know as a physicist that this good thing about this ionic liquid is that as a physicist, I know that viscosity and mobility are inversely proportional to each other. So my focus is always to purchase the ionic liquid which is hydrophobic, because I do not want any electrochemical reaction in between polymer and electrode, means dopant. And the another one thing is lowest viscosity. So now these days, too many ionic liquids are available. You can purchase from company, but be careful for what purpose you are going to purchase these ionic liquid. So my focus is only towards lowest viscosity and hydrophobic in nature. So when I go directly or indirectly the ionic liquid in polymer electrolyte using this common method that is known as solution cost method, what I found that conductivity increases, which I want, particularly for electrochemical devices. So you see the polyethylene oxide, PEO conductivity is nearly insulating our for -8. When we go directly with salt and then ionic liquid in different percent. The ionic liquid, the ionic conductivity raised up to -3 to -4 R. And this much conductivity is, you can say, maybe reasonable point to get a very good electrochemical device. Otherwise, you are going to develop a device, but efficiency is too much good. So what we found that you don't ionic liquid directly or indirectly with salt, conductivity going to increase. There are too many mechanisms, too many science behind that one. I am not going to tell many things. Anybody is interested, we can discuss after this conference or within this conference. Now, using XRD, what we found most of cases, I'm not talking about 100% cases, but most of cases, if you put ionic liquid, their peak intensity goes down. If you compare with your pure PEO peaks, intensity goes down and there is a broad hump. This will show in polymer electrolyte case, put ionic liquid, your crystallinity goes down. It means the morphicity of that matrix is too much high. And it is well known that if you have a Marcus matrix, the ion penetration is easy and maybe fast. So conductivity is going to increase because it is governed by conductivity relation, conductivity property and humidity. To verify this result, normally we have carried out in almost all cases experimental procedure that is known as differential scattering calorimetry. Because as a physicist, this one experiment to give you, this one characterization give you percentage crystallinity. So what we found is giving a very good correlation with XRD as well as a conductivity value. Put ionic liquid, your crystallinity goes down. This is already I have shown using XRD as well as conductivity. Now coming to next one, I think that one is known as solar cell measurement. In our laboratory, we have already, since I have little bit glimpse from, you can say, abroad, Korea, that how we are making a dye-sensitized solar cell. And in our own laboratory, we have purchased solar simulator. So you make a good polymer electrolyte, doped with ionic liquid, and just use as a electrolyte. So normally in case of, you can say, dye-sensitized solar cell or supercapacitor, okay. Electrode is one portion and electrolyte is second one portion. So either you are going to make symmetric electrode for supercapacitor or going to make working electrode as well as counter electrode in dye-sensitized, that one is different procedure. But using same electrolyte, what I want to say here, using same electrolyte which conductivity is too much high, you can sandwich between two electrodes. You can get a DSSC, you can get a supercapacitor. But if you know the basic principle of, you can say, supercapacitor and dye-sensitized, then you are going to do these experiments. Because dye-sensitized solar cell needs redox couple. However, in case of supercapacitor, it does not need this redox couple. So, putting ionic liquids as a redox couple, we have to add iodine to make I minus or I3 minus redox couple, something like that. So, this one is the paper, latest paper you can say with Professor Cairo, we have published in 2024, where we got using another kind of electrode. I am talking about ternary electrode because here there are not too much enough time. So we have made a ternary tailor-made electrode material. Using same electrolyte, we have developed a dye-sensitized. So this is reasonably good. I cannot say that it's giving maximum efficiency, but during large, you can say large number of experiments, what we found is in polymer electrolyte, PEO doped with ionic liquid or salts, we are reasonably good getting conductivity point of view along with once an efficiency of, you can say, 4% in case of polymer electrolyte. Although it's not too much big, but 1 by 1 centimeter is very important for that. So kind of, you can say, importance of ionic liquid in this platform, which I want to say that ionic liquid in conductivity case, this conductivity relation is governing whole ionic conductivity relation. conductivity is equivalent to mu. So this conductivity is like Q is constant. Everybody knows it's a Coulombic constant. So either you can write it in N or mu. Mu is directly related with our viscosity. Mu is known as mobility. So if you put ionic liquid, you are getting more amorphous matrix. It means your mu is going to increase. And if this one is going to increase, your conductivity is going to increase. Yeah, because ionic liquid is solidly composed of only cation and anion. So whenever we are putting ionic liquid, we found that this N value is going to increase. So ionic liquid property can modify, can maybe satisfy with this equation, and we found that ionic liquid is a very good dopant in case of conductivity. If you want to increase in conductivity, it's working as a plasticizer where it reduces crystallinity. Along with that one, it's provided more iron. So in both cases, conductivity is going to. So these are my foreign collaborators. Let me thank, because this one is the international conference. So I have a long collaboration with foreign people where I really think what I learned from marine session, that collaboration is very important. Whatever I got, it's not my own, you can say, credential, it's by these teachers. I can say that this is Professor Hugh Lee, where I passed 4 years in South Korea, and he is Samsung Display Group President right now. Norway, Professor Enar, he teach me something about, you can say, solid state supercapacitor. And this is my Russian collaborator, France collaborator, Malaysia collaborator, and Brazil collaborator. So we have too many things. And using another kind of things which I want to show in front of all of you, that in Sada University during COVID, this only takes only, I think, 1 to 2 minutes. What we have done, that we have just collected plastic bottles which thrown inside the campus, and we have processed it, made it reduced graphene oxide, and using same, you can say that reduced graphene oxide, we have put it in electrode material, and we have proposed this government that it may be clean, because that time there is Modi mission that everywhere we want clean India, so we got CSTP project on this particular topic. This one is my last slide, because I am also going to organize a very beautiful conference. I can say very beautiful because it's conference in nearby, you can say, Delhi, and we are going to take a visit to Taj Mahal, where most of India, you can say, abroad people want to like this one. So I invite all of you to join this gathering in January. And now this one is my strongly, you can say, collaborators. Thank you very much.
Thank you very much, Professor, for taking the time. And I'm really happy the way you have presented the excellence of your department, and what are the main your projects you are in progress under your supervision. And moreover, the way you have presented the importance of electrolyte polymer. And then, above all, I am happy to see the latest paper that you have shown there, and because of the IP technique and the role of this ionic liquid that the dopant that they are playing in the conductivity. So I think it was a very good presentation, and this subject can be taken further also. As a such topic, any research student who would like to take PhD work, I think this is a good topic to undertake. Okay, so once again, thank you very much for your very good presentation. So I now request the audience to ask any question if they have. At least one question must be asked to Professor Singh. Because he has given a very good news also that he is going to organize his international conference.
Yes.
So that will be just after a week or so. No,
No,
it's the first week of January. So it is a good opportunity to visit Delhi, and then to, of course, he will make an arrangement to take you all who will be present there to the Taj Mahal also. So we must thank to him for that very good news also. But the fact remains that you have to ask at least 1 or 2 questions. We have time.
Yes.
Yeah, please.
Ionic whether ionic liquid,
So you can answer from
it solubilize and so there is decrease in crystalline percentage crystallinity.
No, sir. Ionic liquid, what I know, because I have already told you in earlier case, we just purchase ionic liquid. I have not synthesized ionic liquid. What I got from literature or ionic liquid books, there is a very good book with Professor Ono, who is originator of these ionic liquids. In that book, it's written. This one is in earlier case, it's known as eutectic salt. Chemistry people know better. Eutectic salt is those salt where you can take two salts and you mix it. If their melting point is lower than whatever individual melting point, it may be treated as eutectic mix. Now people have discovered too many ionic liquid which is hydrophobic in nature. It depends that what you want with your polymer electrolyte. I have already told you. If I am taking any ionic liquid, which is not will make friendship in my polymer electrolyte, let us say, in place of giving good homogeneous film, it's going to be precipitate because it is going to take another one chemical reaction. So ionic liquid point of view, it's not eventually it's proposed as a solvent in earlier case. In place of acetone, people proposed it. But since it's a caustic in comparison to organic solvent, let us say ethanol, ethanol and other things. But nowadays there are too many cheap ionic liquid. But of course, you must be clear where you want in which form. So I have just purchased ionic liquid.
Sorry to interrupt you, but I think Professor Singh, he is around today or tomorrow.
Yeah.
But if you have any additional inquiry, you can talk during the coffee break or something.
Sure.
Yeah. So please join me in thanking Professor P.K. Singh for very good. Now we have two oral presentations. So the number one is the oral presentation number one that I think will be given either by Dr. D.K. Singh or R.K. Verma. So I request whoever is present among you, he can start his presentation, please. And if the author of this oral presentation number one is not present, then we can go ahead with the second oral presentation. That is, what is it? Oral presentation. Okay. So you want to come? Yeah, please come. Please give your introduction yourself and then about your life. Please come.
So, good afternoon everyone. I am Devansh Arora. Starting with my introduction first, I am Devansh Arora, currently project associate under Dr. Naveen Sharma in CSR Chandigarh. So, I am starting this presentation on a topic that is advancing diabetic care, deep learning for precise DFU detection. So, it's an absolute honor to speak in front of you about the topic. As we all know that diabetes is a growing global health challenge. It affects millions of people and brings with a range of complications, some of which can be life altering. Among these complications, DFU, which you can say diabetic foot ulcer, which is a major problem. The probability of DFU, you can see in the picture that this is a picture of a DFU foot. This is diabetic foot ulcer. The probability of diabetic foot ulcer is about 50 to 25% of diabetes patients in their lifetime, which is a big problem because in this problem, in a severe condition, they have to lose their feet, called amputations, or maybe some allergies, affections can be happen to them. To solve this problem, we have a solution. First of all, we talk about the problem statement. Currently the solutions or the there is no solution for solving this DFU. Currently there is a one solution that you can identify this DFU in their initial stage. If you skip that or you don't identify this DFU in the initial stage, you have to amputate or lose your feet in last. So it's very important to don't ignore this problem and solve this and identify in an initial stage. Now that but we have a new solution, or you can say that we are working on it. It's in a research phase. Our objective to in this solution is and thermal imaging, and by combining with AI, you can create a cheaper solutions for clinic to identify this DFU, so that patient do not go in a hospital which is far from his home. He can go to clinic and identify this problem and solve it, because precaution is better than cure. So starting with the methodology part, you all know that in AI in methodology part there are mainly three steps: collecting data, second one is pre-processing, and third one is running AI models. So first of all, talking about data set, we actually collected this data set from the PGIMR under Dr. Ashutosh Togi sir. Dr. Ashutosh Togi sir is the, you can say that, head of the diabetic foot ulcer committee in all over India. He also participated in this research. So this data set is of 33 non-diabetic and 71 diabetic patients. 71 diabetic patients and 33 non-diabetic. And this data set is collected from two types of camera. First one is E5 camera and second one is E60 camera. E5 camera, you can say that its pixel is 160 into 120 pixel image, and FLI E60 camera creates the image of 320 into 240 pixel. Uh, Coming back to the data set, by collecting this data, first of all, we give a 15 minutes rest to the person before taking the photo, and after the rest, he also fasted for 2 hours, so that the thermal images come clear, because you all know that digestion system disturb the thermal images. Coming to the pre-processing of the images. We don't use the raw images directly. So first we have to clean the image, reduce the noise, and after that we have to isolate the fit of the image from the thermal image, so that we can create a ROI, or you can say area of interest. Okay. After that, we enhance the dataset by applying techniques like flipping, horizontal flipping, or rotation, and which is going to know about the argumentation, which is important to make the model robust. After that, we come to the training of AI models. As we in this research, I used both machine learning models and deep learning models to compare the results. I use the latest modern methods, which is 16, ResNet 15, mobile net V2, and also compare with the old models like KNN, or you can say ResNet. Sorry, not ResNet. Logistic regression. Coming to the results. This is the results I got from my research. As you can clearly see that in this key points that I covered in this research, that E60 accuracy is coming better than E5, which is obvious because E60 camera has high pixel values as compared to E5. And if you can see that ResNet 50 got the highest accuracy, that is about 0.97 in E60 images, which is, you can say that it's mostly from 100 images, it can detect 97 images in correct way. and also comparing with mobile net V2, which is also important because mobile net V2 have a very low you can say storage space, so it can use in a cheap processors or mobile apps to compare, and can be used in a clinical usage or home apps like this, so that you can identify DFUs. After that, these are the key findings that I already told you about, that the 97.4% accuracy is got in ResNet 50, and mobile net V2 also get high accuracy. So I will tell you why this matter, why all these things are matter. So first of all, prevent severe complications like amputations, which can have devastating physical and emotional consequences. Secondly, reduce healthcare cost. I already said you that today's traditional ways to detect the DFUs are very costly. To make this cost lower, this is a proposal model which is very cheap. Then after that, to improve the quality of life, losing a food is making you dependent on others to work, which will make a people or person to emotionally got very down. So after that, to complete this, there is a last conclusion about this. To conclude, technology like thermal imaging and AI is realizing the way we approach diabetic care. By making early detection of DFU more accessible and accurate, we can transform the life of millions of people living with their diabetes. These are the reference and acknowledgement of this paper, and I'm concluding my presentation here. Thank you for listening.
Thank you so much. I don't know ABC of this topic, and I pray to God that none of us should get this problem. But I am very happy that you have introduced this DFU topic, and you have explained how the camera like E5 and E60 can give you the higher accuracy and all those things. But I would like to ask you, you said that the cost is very low to detect all these things in advance. What is the approximate cost, or is it free of cost?
No, sir. Actually, what you need in this only thermal cameras and the deep learning, which is currently are in research to get a better and better accuracy. But in today world, we are if a person, doctor about to know that he has a diabetes or not, he has to do multiple tests. And in DFU also, he has to do multiple tests like mass ratio, muscle ratio, fat ratio, and other things. They are all 6 to 7 tests. So these are the one solution.
Nothing is free.
Nothing is free. It's must
Because in the European countries, for example, I come from Italy, so there everything is free. You are not supposed to pay anything. Okay. So I pray to God that even the government of India, if they can give this facility, because in India there are millions and millions of people who are suffering from this problem. Because nobody denies sweet, even during the lunchtime. If somebody is not even hungry, even then he will take the sweet. So this is our habit in our blood to eat these things also. So I pray to God that you must take care of yourself, because this is a very bad disease. So thank you very much for giving some.
Yes, thank you. It's my honor to speak.
I was really wondered that how this topic entered in this conference, but maybe this is a multidisciplinary topic of the conference, so that's why they have included this topics as well. But we are happy to learn something new from yourself. Thank you very much.
Thank you very much.
Now is the time for the second oral presentation. I don't know if Mr. DK Singh or Arya Verma is around. Not present. Can we wait for some time? He's not present at all. We can close the session, sir. Okay, sir. Thank you so much for your patience and time. So I think all of us enjoyed something, and we must have learned something new, also, especially what is diabetes problem. So all the lecture or other lecture, they were also very good. Especially, I am very happy to see the latest result that were presented by Dr. DK Singh, because it is very rare that because if it is a research paper sort of thing, then the people they present their researches, what they have done in the research part. But if it is invited talk, then most of the time it is sort of review type of things. But it was really very good to see that how he presented the result that he has just published in 2024. So compliment, and I wish you all the best for your future work. thank you all. Thank you very much for your time and cooperation.
Thank you everyone. So it's time for IT from 4:20. So you will have to wait for 5 to 10 minutes. Yes, sir. Thank you, sir.
I think it's better to work with IT, you know. There are too many things we have as teacher also say. Very good, your account. There must be break or somebody is. No, it is just a business of time and waste of money and all. Yeah. Anyway, we cannot do anything because we have to follow the rules and regulations that have been set by the organization. And we are happy for that. At least they are serving us. They are not taking anything from us.
Thank you everyone.
लास्ट में गुलाम साहब 5 में लोग थे मिस्री
कुछ आ गए होंगे इसके सामने
वही
वो हो गया अभी लास्ट वाला है खत्म यहाँ का सेशन
शायद
ये सब तो निकल गए।
नहीं कुछ वेट करने को बोला
One day we will begin work.
devices like we have solar cell, wind wave, biomass, but we can't carry these devices in our pocket to power the LEDs, to power our mobile phone, our electronic gadget. So idea is to develop some kind of the portable devices that can power our daily device by just mechanical energy. So how this can be possible? So this is basically based on the piezoelectric phenomena. We know that some material which is a piezoelectric material, and if we apply some mechanical stress, we can create the electric dipoles, or we can create the electric field. And those material is basically having the non-centrosymmetric phenomena, crystal property, like zinc oxide, SiO2. So here we consider the zinc oxide. If you apply some stress, compressive stress or strain, so there is a relative displacement of the zinc cation with respect to the oxygen's anion, which create the electric dipoles, permanent electric dipoles in the C direction. And this is the origin of the piezoelectricity. Many other materials are also there, like lead zirconium titanate, barium titanate, right? Gallium based synthetic materials. We have some polymer also like PVDF, PRE. So those are flexible piezoelectric field. So whether we can convert these piezoelectric materials or nanostructures in the nano devices, flexible nano devices. So this can be possible through the integration of these piezoelectric materials in the nanogenerator form. So like nanogenerator is a technology, if you create the mechanical energy, it will generate the electricity. Okay, like a piezoelectric material here, you apply the external electric field, you can create the mechanical deformation within the materials. So some year ago, this Professor Jungli Wang from Georgia Tech, what he did, he grew this nanowire, this nanowire on the like a conducting substrate, and then he used the piezoelectric force microscope, and he just observed that when there is a negative and positive charge developed on the nanowire, there is a formation of the Schottky contact here at this junction, where he got this blue spikes. Basically, this is the presentation of the current. So current can be obtained when there is even small mechanical deformation. So the novelty in the piezoelectric nanogenerator is that it has no limited lifetime. Once you have mechanical energy by wind, by pressing, then by sound waves, so all those can be used as a source to generate electricity. But you know the batteries have a limited lifetime. Also the size is not flexible. We can get the flexibility with the nano generators. Even it is having a small output power, but we are enough to produce high output power from our devices. Like some of the fascinating example is the pacemaker. Like maybe after 2 years or 3 years, the patient has to replace the battery in the body, and he has to undergo like again surgery to replace the battery. So even we have having the nano generator, we can power up it through the blood flow in our body. So no need to change the batteries. This nano generator can fulfill the requirement of the electricity to power the pacemaker. Like the road we are adding. So we can construct the piezoelectric nano generator using the cost-effective materials, and then we can connect them in the series ways, parallel ways, and then under the motion of the wheels, we can create the pressure that electricity can be stored in the capacitor that can be used to power the LEDs and street lights. Even. So it means that by breathing, blood flow, wind, wave, these all energy can be converted and can be used as a power for sensor application, for robotic application, for any devices. Now, what about the flexibility and transparency? You know, this screen is a flexible, but this part is completely not flexible. It is the hard. So idea is to make this battery part also flexible. So in this way, what we did, we developed the zinc oxide nano
other side. The pristine zinc oxide is having a lot of oxygen vacancy and other defects. So we just passivated those vacancies, and also at the same time we increase the piezoelectric charge coefficient. So we use the cell layer to grow the vertical aligned vanadium doped zinc oxide nanoseed. So you can see this is the SEM spectroscopy, and these are perfectly well aligned vertically. And this is the seed layer assisted growth. We have developed the seed layer initially on the PhD, and then we use the vanadium as a doping element. And without vanadium, it was nano wires. But when we introduced the vanadium, it changed the surface energy of the nanoseed, and it restricts the formation of the growth in the C direction and just allow the growth in the A direction. So because of some shielding effect created by this vanadium hydroxide ions. Now we also confirm whether this vanadium was in which electronic state, V4 plus or V5 plus. Like it is within the nanowires, nanoseed or on the surface of the nanoseed. So we got that the many ions like V5 plus was within the nanoseed and V4 plus was on the surface states. Now, whether the nanostructures was basically showing piezoelectricity as compared to pristine zinc oxide, there is some improvement or not. So we did the piezoelectric force microscopy on the single nanoseed. So for that, the same nanostructures was grown on the platinum substrate, and then we apply the electric field from the AFM. So there was the mechanical deformation that we recorded through the PFM, and we got the 4 picometer per volt. It was 1100 goody materials, and definitely it was showing the butterfly curves. This is the nature of the ferroelectricity, but we are currently only interested for the piezoelectric property in these 2D structures. And piezo response hysteresis curve. Okay. So now coming to the nano generator fabrication. So we need basically 2 electrodes. One like this nanoseed was grown on the IPO substrate, and another we need one Schottky contact. So we chosen the gold coated PES substrate. Like gold was coated on the plastic substrate so that the whole device should be flexible and also like transparent, at least this zinc oxide nanoseed. Now when we are applying the mechanical pressure, you see the negative and positive voltage was created here, right? And this positive pulse we got. Once we are releasing the pressure, like we have a computer controlled force simulator where we can apply the force in a controlled frequency, in a controlled Newton, and then we record the output voltage or output current from our electrometer. Now you see the current was almost 1 microampere per centimeter square, is very high. Now once we are releasing the pressure, so it should be a negative pulse here, but it is not coming. It is coming in the DC kind of the nature. So why DC kind of the output voltage? Because see, once we are applying the pressure, this electrons is coming to the bottom direction. Okay, but when we are releasing the force, this electron is not returning to the top electrode, and then we are missing this reverse peak, and only DC kind of the nature is coming just because of the electrostatic field created by this vanadium atom. So now this is the nano wires and this is the nano seed. So in the nano wires you can see the output current was just 10 nanoampere, and here it was 1 microampere, and also here DC kind of the nature, here DC kind of the nature. So we need basically DC. If we are getting DC output voltage, we can use them directly to power any portable electronics. Now this is a real demonstration of the devices. See, once we are pressing it, here by our finger, we are getting a pulse. Once we are releasing it, again we are getting the electric pulse in the same direction. So how this piezoelectric nano generator basically works and how we can actually integrate them as a device form. Now there was many basically native defect within the zinc oxide nanowire. Like if you shine the UV light, what will be happen? There are a lot of electrons and hole pair will be generated, and these electrons and hole pair will screen the piezoelectric potential. Okay, so we also passivated this native defect by the thermal annealing, so that we can get output voltage even constant under the UV light. This is the harsh conditions. So to do that, we did the thermal annealing of these vertically aligned nanowires grown on the Al2O3 substrate, hard substrate, and we control the defect. And then output voltage was given constant in different UV light intensity. Now, it is very hard to grow the nanowires vertically on any substrate. It depends upon the crystal structure of the materials, their vapor pressure of the materials, and but it is very easy, I can say, easy to get the nano powder and even the solution form of the nanomaterials. Okay, so how to use this nano powder and nanomaterials in the device fabrications? And also, since we need the piezoelectric material with very high piezoelectric charge coefficient, so we chosen the zinc silicate, which is basically shows the two kind of the crystal structures, centrosymmetric also and non-centrosymmetric also. So we are interested for the non-centrosymmetric property. So we control the growth parameter through the hydrothermal technique, and we achieve this kind of the randomly distributed nanowires. And this randomly distributed nanowires is having the non-centrosymmetric structures. And then we also do the dielectric analysis to see how much energy can be stored in the nanowires. So see, it is showing very high dielectric constant, even the 20,000 with respect to the bulk dielectric constant. It means the charge storing capacity is also good. Now to visualize the piezoelectric charge coefficient, we did the piezoelectric force microscope and also the phase image mapping. Like once we are applying the negative field and once we are applying the positive field, we can see the dipole change within the single nanowires. Here, this is the positive electric field, this is the negative electric field basically, and this is the showing very high piezoelectric charge coefficient, about 117 picometer per volt, very high as compared to zinc oxide. So the origin just we have discussed. Now here we have the powder. We need electrode that must be transparent and also flexible. So to use that transparent electrode, we utilize the graphene nanosheet. We know the graphene is a very high conducting materials. We will not go in that detail. And growth of this graphene is also very interestingly, we can achieve the large scale growth of the graphene through the CVD technique. So we utilize the CVD technique to grow the graphene on the copper coil. So we control the gas and other temperatures parameter to achieve the monolayer graphene on the copper coil. Now, next task was how to transfer this graphene from copper coil to any substrate. Then only we can get the devices. So we did the wet transfer method, like copper we etch out to the wet chemical route, and then we transfer this graphene on the PET substrate. This copper coil was etched out through the solution, and then this is the final diagram of the device. This nanowire, these silicate nanowires are randomly distributed in the PDMS polymer matrix. This was randomly oriented, and this is the graphene we transfer on the PDMS substrate. First we transfer on the PET, and that was mechanically integrated on the devices. And you can see here, like this nanowires were randomly aligned basically. Now, the performance of the nano generator. So we applied the very little pressure, 0.05 kg 0.15 kHz, and then furthermore, and we got the voltage up to 8 volt. In the case of the zinc oxide, it was few millivolt only. So many times improvement in the output voltage was here, and also it was in the polymer matrix. So mechanical durability was very high. And this is a reverse test of the nano generator, just to ensure that see here the signal is in the positive direction, and here the signal is in the reverse direction. It means if you change the connection positive to negative and negative to positive, you can reverse the signal of the piezoelectric electric signal, just to ensure that it is from the piezoelectric phenomena, not from any other source. And now we also compare the performance with the ITO electrode. So see, in the ITO electrode it was just 1 volt, and with the graphene it was very high. It means that charge transport phenomena was also efficient at the interface of the zinc silicate and the graphene. And since the device was flexible, so we can fix the device in any part of our body, and just we can sense it. Okay, 5 minutes. Up to 5 to 10 minutes. Okay, so this is also showing the very durability. Like you see, the current density is highly durable. Like even up to the 700 cycles, up to few thousand cycles, there is no change in the intensity of the electric signal, and the conversion efficiency was 29%. Yeah, you can see once we are applying the pressure, we can power up the LED directly just by pressing the device. No external electricity, just mechanical energy. Okay. This work was also published in the Nano Energy recently. Similarly, like we also observe very high dielectric constant, band gap reduction. So we used to publish in some of the papers. Recently, you also saw this kind of the news that if you walk on the floor, you can create the electricity. So this kind of the work we also done it. Like we developed the 1 feet by 1 feet polymer matrix based on the piezoelectric nano structures, like nano cubes, so that alignment can be controlled. If it is a nano wire, it is a randomly aligned, but if we have the morphology with the nano cubes are spherical particles, so their orientation can be easily controlled, and even if it is randomly aligned, due to the morphology, it will show the high piezoelectric polarizations. So we increase the pressure, we change the concentration of the device, and when the curve is rolling up, it is generating very high voltage, even to 25 volt. And if the device is passing very fast, the FWHM of this will also vary. So it means you can monitor the speed of the any nickel just by the electric pulse, their FWHM. So not only for the energy, for the self-power sensor application also it can work. Similarly, for inside our body, like we need the biocompatible material to power up the medical devices, sensors, just to the blood flow. So not all materials are biocompatible, right? So what we did, we take in the chicken egg is, and then we broken it, and then we peel off the membrane. So this membrane is basically nothing but a biocompatible materials which is having the intrinsic piezoelectricity due to the collagen based piezoelectricity, like protein based. So what we did, we taken this XL membrane, we deposited this XL membrane on the pristine ITO substrate, and also same time polymer film, and then we have deposited the axial membrane over there, and then two devices we have formed, like interface pivot layer, and one with the axial and one with their heterostructures. You see, very interestingly, it is giving the 15 volt. Just small pressure will give 15 output voltage. So there was the chemical interactions and there was the interface polarization between the PVDF and axial that we have discussed. I will not go into that detail. And just also it got published in the journal of the anyway. So these devices was able, like polymer based or inorganic material based. We can easily get the output voltage, output current, power density. But what happen in the water condition or in the like humid condition, whether they will sustain. And similarly, like PVDF polymer, this is the piezoelectric, we always need electrical cooling so that the electric diodes can be aligned and you will get the high output current or voltage. And so with HARC, let us control the density of the PVDF and also introduce the carbon nanotubes within the PVDF so that local polarization can be possible that will give the fitter phase as well as we can get the lightweight materials like density we can control, foamy kind of the materials. So we added the NaCl salt. So salt is added with the PVDF and carbon nanotube, and then we immerse these devices in the water so that NaCl will be dissolved, and only this PVDF with CNT kind of the foam we will get it. And this is a purely hydrophobic material and also having piezoelectric property 9 kilocoulombs per meter. You see, these pores are because of the NaCl. NaCl was lost out in the liquid. And this is the carbon nanotube which is present inside the PVDF matrix, and it helps PVDF to create the more beta phase, which is very essential for piezoelectricity. Now, here we set up one of the experimental plant where we created the humid condition, different relative humidity condition, and we measured the output voltage up to the 75% of the relative humidity condition. You see, even up to the 60%, the output voltage was stable, like 9 volts. And this is just because of the hydrophobic nature of the PVDF. So, in the raining condition also, within the presence of the pressure coming from the raindrop, will also able to create the electricity, and that raindrop will not damage the performance of the nanogenerator. But the problem was the high surface energy of the carbon nanotube. They easily illuminate actually. Once you introduce carbon nanotube, they will illuminate, they will not properly disperse in the PVDF matrix. So with HARC, let us control the dispersion of the carbon nanotube in the PVDF matrix and also enhance the mechanical strength of the device. So for that, we developed the copper and nickel nanoalloys through chemical approach, and this copper nickel nanoalloys we introduce within the carbon nanotube. And we can see here, this copper and nickel was inside the carbon nanotube. So it reduced the surface energy and also allowed to connect all CNT well together in a better way. And so like PFM measurement also shows the very high electric charge of the cell up to 160, and see the output voltage 40 volt from this film just within the presence of the 10 kVA force. And it is also having very high dielectric constant as compared to pristine or the CNT based PVDF. Now, even up to the 1500 cycle, this copper nickel decorated PVDF film is very high durability, whereas only the pristine is degrading the output performance even after 500 cycles. So it means if you perform the stress versus the strain curve, like the young models, Okay, this work was also got published in Advanced Material Technology. In a similar way, we can also harvest the thermal energy into the electrical energy, like thermal gradient, by the means of pyroelectric phenomena. So, like air conditions are heat coming from the CPU, and any thermal gradient, if you are having anywhere, you can convert them into the electricity. So, some of the piezoelectric materials also show the pyroelectric phenomena. Okay. So in that way, what we did, we have developed the stretchable devices.
So,
This is
yeah,
yes.
I think your time is up, so if you can wrap up in a minute or two, that would be good.
Thank you, sir. I will finish in 1 minute.
Okay.
So this kind of the stretchable devices we have developed by using the graphene at the top electrode and carbon nanotube at the bottom electrode, so that heat directly can actually change the electric dipoles within the system. And at the same time, like pyro and mechanical energy, both can be integrated together, and that can be wearable also. You can basically wear it. Okay, so time is very limited, so I am going very fast. And similarly, like MOS2 nano sheet, we developed a two-dimensional MOS2 nano sheet, and we dispersed this MOS2 nano sheet in the PDMS polymers, and see, like using the carbon nanotube, conducting carbon nanotube at the top electrode will increase the current density basically. Initially, the current density was just 1 microampere, but with this condition, we got the current density of the 10 microampere per centimeter square, very high. And this is just because of the hexagonal freeze in the 2D materials.
So please conclude your talk. We are out of time.
Okay. Okay, thank you. Thank you, Sadiq. And that is coming up the thank you. Thank you all for giving me time.
So in the interest of time, we will see if there is a question from audience. One question. Anybody? Okay, so what kind of output you are getting? I know you are getting very high voltage, but the current is very, very low for practical application. So can you comment on the total power output with your thermal, the
Yes.
triboelectric
Yes.
generator?
Yes. Basically, here we have obtained the current up to the 10 microampere per centimeter square, and definitely up to the 100 microwatt we already achieved with the MOS2 samples. Definitely, the power density is a challenge in the piezoelectric nano generator, but it can be controlled by the choosing the right piezoelectric materials and right electrode, and we achieve up to the 100 microwatt per centimeter square.
Okay, thank you so much.
Thank you, sir.
All right, so we are going to move on to the next speaker. So the next talk is by Dr. Hasita Mahabaduge. I hope I pronounced that right, from Georgia University, USA. So again, in the interest of time, I will skip the introduction of the speaker and turn the floor over to you. So Hasita, please go ahead with your presentation. Thank you. Here they are three. He's not there?
He is not there. He might be joining. Yes.
Oh, there it is. Okay. All right, let's get started.
Start.
Is it on full screen?
Yes, sir.
Yeah.
You can start.
Okay. So then the discussion is on perovskite solar cells. Let me quickly start with a brief introduction to solar so that everybody is on the same page. And when we see solar energy, what we see on rooftops or in large scale fields with
research or our research on perovskites, we are talking about the small scale solar cells, which, and usually when we talk about solar in general, it consists of N-type and P-type PN junction, the simple basic for any sort of an electron, and PN junction, and then we have protective layers, mostly glass. And a quick introduction to solar cells, how it works. When light comes in through a material, it can either reflect, transmit, or get absorbed. And when the absorbed light, the energy of light get absorbed, it would part of that energy can get absorbed by the electrons, and then they can get excited. And this electron now has more energy. So when this happens, we can use this inside material called, and which is the photovoltaic effect, which is the photovoltaic effect. So then in simple terms, what would happen is when light comes in, it would generate the electrons, and then those electrons, if we can let them flow in a preferential direction, then we can use that as energy. So this is a very brief introduction how a solar cell works. And then most common when we look at a rooftop or when we say a solar panel, it's highly likely that solar cell is made out of silicon. The reason, again for historic reasons, that silicon is the material that we've done a lot of research. That's the reason why we have our phones, why we can do this communication. And therefore solar also started, and still its most common material is in silicon. And back in the day, in the say in the 50s, 1950s, it was developed for space programs in the US and in Russia. And then what was important about that is it has a long lifetime. And however, we'll talk about it a little later, the absorption coefficient is higher for silicon, what does that mean? Higher absorption coefficient means that you need relatively more material to absorb the same amount of energy, say compared to the different solar cells that we are going to talk next. However, the single crystal solar cell has around about 25% efficiency, and to create single crystal solar cells, you need more energy, say compared to polycrystallines, where although the efficiency is low, but the cost to create amorphous versus polycrystalline versus single crystal is higher in that direction, where single crystal, to have less amount of defects, we need to spend essentially more energy to build that as well. And one other challenge with the single crystal is they are rigid and brittle, so that it limits the potential for applications. And then, as I said at the beginning, most of the time when we talk about solar cells, it is a N-type and P-type material. So then we could get using same silicon. If you dope it with say phosphorus, we get phosphorus or boron or gallium, then we can get the N-type and P-type material in silicon itself. And just to give a quick overview that this is something obvious that we all know, that some of the challenges with solar energy is they do not work at night or in cloudy weather, so we need to have a storage. So if you are listening, if you are an aspiring scientist who's listening, the next frontier, although I'm working in solar, but next frontier in energy is storage. You just heard of a great talk earlier as well about storage, so then that is the area to invest your time and, for that matter, money. The reason most of the economies, most of the countries now spend more money in their research and development in energy storage rather than the energy generation. But it is important that we continue the strides that we have made in energy generation in solar cells. And one other thing is that if we assume that the energy is 20% for a given solar cell, most commercially available solar cells are around 20% or so. So then that means that incoming energy, say 100 watts per square meter, only we are using 200 watts for electricity, whereas the 800 watt is, in this sense, is wasted as heat. So then again, there are some applications that if you can think along those lines. Then in my talk, I would like to guide you different directions that if you are especially young scientists thinking of what to do next, then energy storage might be an area to work. That's where most of the government funding is. And then energy generation, when it comes to energy generation, how to reduce these types of waste. We call it waste because it's not generating electricity, but how can you use that to for your benefit? Those are some of the things to keep in mind and start thinking about it. So when it comes to energy generation, the key challenge as a scientist or as a physicist, that's what I have, or that's what I'm working on to improve efficiency. There are different matrices, that efficiency being the first one, and then we have three other matrices: the voltage, open circuit voltage, short circuit current, and field factor. And then you can dissect that into the third level matrices as well. But efficiency is something that all of us would understand. That is, in terms of a solar cell, what is the amount of sunlight it received and what is the amount of electricity it produced. So the new solar materials, they need to be efficient, and we reached that back in the day earlier, but it was not inexpensive, so that normal people like us who are not very rich can put a solar panel on our rooftops. But now it has come to a point that even in most of the countries, at least in the developed countries, the middle class people with middle class income can put rooftops on their roofs. So then it has become inexpensive, and that is something that we need to move further if we need to make it open or available for all people. And then comes the issue with some of the materials that we use are not earth abundant, so then can we try with earth abundant materials? And then some of the materials, especially the second generation solar cells, they use cadmium, and then perovskites that I'm going to discuss, they use lead, which are considered to be toxic material. So then we try to avoid those, either use them and recycle them, or we need to think along those lines as well. Not just improving the efficiency, but then how we can improve the efficiency while keeping the cost down, and then making it available for essentially solar energy for all type of a team. And then, so silicon is still the most common material, but we came a long way trying to replacing silicon, and we started with these are some of the examples: dioxide solar cells and organic quantum dots and perovskites. These are the new, or some of them are what we call the third generation solar cells, considering silicon to be the first generation solar cell. Then came the second generation solar cell, mostly the thin films, cadmium telluride and CIGS. They are the leading thin film solar cells, where cadmium telluride made it to the market and is one of the leading thin film solar available right now, and one of the US-based company, First Solar, is the leading manufacturer for Candee solar cells. And let's briefly talk about some of these new generation solar cells, starting with the quantum dots. And one of the advantages of quantum dots is that they have the tunability in the band gap. Band gap is important. If you recall the very first one or two slides, that whatever the sunlight that gets in or hits, then it needs the electrons, it needs to create electron hole pairs that would then get separated. To create that electron hole pairs, you need to match or have a band gap that is sufficient enough for the electrons to make that what we call the jump from valence to conduction band. And for that to happen, we need to have a specific band gap. When it comes to band gap, the thin film material cadmium telluride has the perfect band gap that matches the solar spectrum, And when we work with quantum dots, for example, and for perovskites, we have the ability to change the band gap, in this case by changing the size of the quantum dot. And disadvantages again extremely extremely toxic. And then came the organic PV, and one of the advantages of organic PV, they can absorb light and then create electron holes, or what we call the donors and acceptors. The advantage also is flexible, can be deposited on different materials, and you can think of many different combinations, and most importantly, it is inexpensive. So remember, either to address the question of efficiency, we could go with the high efficiency and also try to make it inexpensive so that it can be used by most people. And then however, the disadvantage is not necessarily the low efficiency, but very unstable. They are very unstable, and low efficiency is an issue as well. But again, with time, people can, or scientists can work on the efficiency part. So then, however, but one of the disadvantages we have is that they are not stable. Remember, silicon, technically speaking, silicon would last forever, because in a solar cell, there's no component that degrades over time. Because it creates electron holes, which goes through the circuit and then comes back or comes back. So then, essentially, there's nothing that, theoretically speaking, there's nothing that degrades. So technically, or theoretically speaking, a solar cell can work forever. But in real life, with the climate conditions, with the conditions of atmosphere, with the conditions, it can only usually usually they give about 20 years for of a guarantee of and however, with organic PV, we cannot still manufacture in mass scale because of the issues of the stability, and that is the same issue we have with before that the dissected solar cells are also a competing solar cell. However, it has its own challenges where you have low efficiency still around 12% or maybe the 13% very recently, but they are very low in efficiency, but these are easy to make. And then the most important thing is they are semi-transparent, meaning as you saw in one of the pictures earlier, this could be used for example, high-rising buildings for windows, so that you are still letting some of the light come in, but you are using part of the light through the to make it look nice as well. And of course, they also work in low light. But then comes the perovskites. When we say the word perovskite, it means that it is a material with the specific structure, what we call the ABX3, and most common being the methyl ammonium lead triiodide or methyl ammonium lead iodide perovskite. And one thing that obvious is that you can see that it has lead. It's the disadvantage that we are going to talk next. And also, still, the stability is an issue. Although there are they are trying to commercialize the perovskites at this point. There are a few industries that's coming up. And however, the advantage is, remember, silicon at the CIGS, they took a long time to reach the efficiencies of 20%. But perovskite, within very few years, in less than 10 years, they reached the efficiency of 25.7. So then, and now it's slightly higher than this. And one of the things that I discussed are the quantum dots can also be used here. They also have the variable band gap, that is, can be designed for specific applications. And then the current trend with perovskites is to use them in tandem with either silicon or CANDEE or CIGS to be used as tandem solar cells. We'll briefly talk about that as well. And this is a little bit of history about perovskite. And this is the Goldsmith tolerance factor, which is in simple terms, I'm not going to discuss all of this graph, but in simple terms, if you can say this is a cesium lead iodide and formadium lead iodide, you can see on the top formadium lead triiodide, and then on the bottom we have the cesium lead iodide. By changing the size, in this case effective radius. Effective radius, you can change the tolerance factor, and then you can also make some changes in the band gap as well. So then you have a lot of options, because if I go back, we are talking about ABX3, where you can use many, where you can use different options. You have options to work with, so that you can make a good choice. What would be the best option? And either playing with lead, tin, germanium. This is a grid showing some of the materials, the metal, lead, tin, germanium, or iodine, bromine, chlorine. So with this, then you can look for what properties are you most interested in: defect tolerance, excited binding, or the stability, band gap. So based on that, you can try different options with cesium or methyl ammonium, formadium, so on and so forth. And then we've selected our researchers in the past, selected some of these, and then they've avoided some of the other, because some of them did not have any of the qualities that we were looking for. And then the cesium had most of the qualities that we were looking for, but then there's lead. So then back in 2017, nothing was there with lead free. So then that's what it led to do more research in the lead free, to making lead free perovskites.
Hello, Asita, we are running out of time.
Within the same given parameter range, you can work with different materials. You can generate different materials and have a tunable band gap.
Hello,
So
Asita,
then,
hello.
yes.
Can you start wrapping up your talk? We are out of time.
Yes. Okay. All right. So then, and just to update that, at this point, the next type is making the bifacial single junction solar cells, and where you can use the light coming from both ends. And then I think I'm going to stop right here, just to giving you what is the most up-to-date status of perovskite solar cells, and where with bifacial solar cells you can go with theoretical generating about the efficiencies. Thank you.
Thank you. So this talk is open for questions. Anybody has any questions on the perovskites or any of the solar cell materials that he has presented? No questions? Okay. So maybe I'll ask one question. So what is the role of, of course, you mentioned that a lot of it is going in terms of heat, right? Only 200 goes into useful energy and 80 or 800 goes into waste.
Right.
So how do we minimize that? I mean, what is the latest on phonon engineering in perovskites to reduce the 800 to 600?
So, right. One option is to use the bifacial. That's where I kind of concluded the talk. Bifacial, where you can let some of the light that is reflected to be used from essentially from the backside of the solar cell as well. So then anything that is going away, that you can kind of reuse. But that is the way of doing that.
Okay, thank you so much. I'm sorry we're running out of time, and so thank you for joining us. All right, so the next talk is by Dr. Manoj Kumar Patel, and we'll pull up his talk and we'll turn it over to you directly.
My voice is
Yeah,
audible.
we can hear you.
about science, publications, citation, edge index, etc. etc. So by profession, I am engineer and interested on developing the products. So whatever the science in previous two talks, especially previous two talks, Dr. Gupta and Dr. This uh, Harshita, I will talk about translational research, how the science can be translated into products. So my part is on little bit on instrumentation side. Okay, my collaborator has already spoken. Dr. Gupta is my collaborator. He has talked about piezoelectric nanogenerator. I will be talking about little bit on triboelectric nanogenerator, and then indoor light harvesting, and then little bit on hydrogen storage that Dr. Ahuja has spoken in the morning. So I will be talking about totally on instrumentation side. So I'm from CSIR Chandigarh. CSIR Chandigarh is Central Scientific Instruments Organization. We work on instrumentation, irrespective of any area, little bit not into genetic side. Okay, we work on cages, that is head-up display. We work on water, that is patal, you can say. We work on ground-based systems, on agriculture, healthcare, etc. So we work on all three fronts. So what we do? We do societal science, societal work. We do high science. We do on strategy. Our laboratory is strategic sector. And very recently we have initiated so many works. That is the semiconductor mission. This is institutional work. This is not my work. Okay, I'm just giving the glimpse of my organization. So we have academic as well as diploma providing institutes. That is Infosys Training Center. This is the first kind of institute in India that provides skilled manpower to different industries, and all the pass out of this center are basically entrepreneurs, who is contributing to the lot of GDP in Indian economy. I will give you the data. Around 22,000 crore per year contribution to GDP of India. All people are majority on Canada, and very few are going to higher study and all. They set up their own industry. This is something. And Academy of Scientific and Innovative Research, let me tell you about. We have almost 6,000 to 7,000 PhD students, which surpasses any IIT till now, because we count students from all the 37 laboratories of CSIR. So this is a, but in each lab we have 200 or 205 to 250 students per lab. So this is about my lab. So my initial research was based on charged particulate matter. Either it is a particulate matter in solid phase or it is spray phase. So by charging the liquid sprays, you can control the trajectory of charged particulate matter. So you have seen these devices. I have transferred 8 technology know-how till now. Created 3 startups. All the technologies are available in the market. You can Google it. You will find the industry and you can buy. So this is a pesticide sprayer. This is COVID times. We have developed electrostatic disinfection device. And you will see in Delhi there is a lot of water sprinkling going on. So these are the innovations employed in Delhi region to curb this pollution. And the third one is thin film deposition through electrostatic process, that is called electrospinning and all. One is electrostatic spray coating system for fruits and vegetables to enhance the shelf life. So we work on visible coating materials, and then drone based and some automation in agriculture. So this is my base of my work. Now, as I spoken, to reduce the size of the droplet, the electrostatic force will be more, and then you can control the wastage of pesticide or any disinfectant, anything by overcoming through electrostatic forces. So this is something like that I have as a base. Now I'm going to present on little bit something like this in an energy side, because this conference name is energy. So I will be working on indoor light harvesting, nano generator, and hydrogen storage. So these 3 topics are my in my presentation. You can see there is a lot of collaboration involved in my work. So the basic fundamental or to progress, you can say in the morning, Dr. Ahuja said about it. the collaboration is very necessary to excel in science. Okay, and industrial participation is more necessary. If there is no industry, and if you are not able to translate your science into product or some societal aspect, I guess there is no use of my citation or publication. I am not criticizing the publication. I am just giving you some my perspective of science, doing science. So we work with University of Florida in terms of frequency stabilization during COVID-19. We work on air purification through Google University and you can say industry participation. I work on food safety and nutrition. These works on little bit you can say very different from usual science. For example, food safety and nutrition. You must be working on coating material something. But we have developed technology to coat the material to on fruits and vegetables to reduce the consumption of material. You eat right now this bags coating, but we are trying to replace that by through digital coatings. So now coming to the topic of this presentation. Triboelectric nano generator, why we are replacing? Because we are right now we are using batteries for different wearable devices like watch, uh, tablets, etc. So they have some limitations like limited lifetime charging and overheating and fire. Sometimes it catches the fire. To avoid such type of incidences, there is a very recent work on it going around 2000 or something like that. So triboelectric nano generator. If you make a contact on two positively charged driven materials, they are capable of converting mechanical into electrical energy. In previous work, you have learned about piezoelectric. This is triboelectric. Because my background is electrostatic, charging, discharging, so I can easily adopt this research. So yes, electrical charges migrate from one material to another when the two materials come into contact, and this phenomenon leads to alternate current. So now my work starts from alternate current onwards. How it is converted into DC current, DC voltage, and then how it is used in some devices. So I will quickly move the slides because I'm not going to explain on some theoretical aspect of material selection and something. So what is the merits of these devices? Large output power, as in previous presentation, they have 10 voltage, 20 volts. I will be talking about 40 to 50 volts, but current density is 10 microampere per centimeter square. So you can convert into power and then you can drive some devices. So I will be talking about power management system. How such voltage can be used some useful manner to drive some devices. So electronics part matters. Then instrumentation comes. So yes, there are a lot of challenges in these devices. Till now, we will not find any device. There is a lot of work is going on nano generator, but hardly will find some device to drive some kind of. So we are trying to do that. I am in collaboration with Dr. Gupta in previous talk. So you can also harvest biomechanical energy moving of your body parts and something, and discharge food movement. And this is the process of some making some nano seeds and or nano generator. So I'm directly coming to electronics part. This is the movement of LGS based and nano generator. So this is the say output and recorded in. Yeah, this is some synthesis, mechanization and structural analysis, some measurement of properties that are being of. So I will be not. Now I am going to this. Now you have put this 10 and triboelectric nano generator. Now work starts here. Even it is giving 40 volts, you will not be able to utilize 40 volts if you are not working on such electronics. So how to convert this alternate current voltage into DC current voltage and then useful means. So there is a rectifier, you can convert AC to DC, but converting to this rectifier is not pure DC. You have to filter out AC. It's a combination of AC plus DC. Then you are putting a filter Now it is not constant voltage, so you have to put some voltage stabilizer. Once you put a voltage stabilizer, you will get that you can say exact or desirable output voltage from this device. Okay, so this is again power management system for different kind of applications. You can drive watches, but right now what we are trying, we are putting these nano generators on UAVs because there is enough movement of UAV, vibration is there. So we are just trying. We have not yet on some kind of measurement or too much useful voltage, but we are putting and we have proved the concept how we can generate some kind of voltage through drones and we can charge those batteries at that time of flying and we can use, but it is not up to the mark. It is not up to the that voltage which is required for drone driving and all. So, but we are working. So this is another. We can generate this through C waves. We can generate this voltage, and we can drive some kind of devices. And also, Gupta talked about temperature gradient, measure of temperature gradient, and through generation of voltage. So another one is hybrid indoor light harvesters. They are small modules, Dyson style solar cell. For example, nowadays there is a lot of use of LEDs in every cities, and people are talking about light pollution. I hope you have heard about this word, light pollution, and people have started. So we create a problem, then we solve it through our science. This is a very common nowadays. Whatever we are working, we have created the problem first, and then we are solving it. So now there is a word, noise pollution. So, for example, you are sitting here, or maybe you take example of hospital, where there is enough light of LED. So you can harvest that energy and you can drive some kind of devices like in airports, you have seen some type of display system for rates for $1 per piece or something. So this can be dynamic, and once it is going to be dynamic, you have to change manually. So if you can power this device through this indoor light harvester, there is no need of any light, any battery or something. But in the night, you can say there is a question that in the night there is no light in the house, so you can make it hybrid. You charge in the daytime when there is enough lights or battery, and then you can using the night or when there is no light. So this is the concept of indoor light harvesting. This is a collaborative work. Again, I will talk. My work is related to electronic design. IICT Hyderabad and East Trivandrum is working on some Dyson cell site solar cell. They are providing us the solar module and then we are converting into useful means. So what we are trying right now, we are trying to drive a CCTV camera to this power. Till now, we have demonstrated on air purification, air monitoring system, the PM particulate matter in Trivandrum Airport. You will find this device. Okay. So this is something, some technical things. So I will not be speaking about it. So another thing is hydrogen generation and storage. All people are working nowadays hydrogen generation, and then there is a problem of storage because people are storing on high pressure. So we are having some metal hydride based, you can say reactor. You can store in the form of metal hydride, and it's a kind of reactor. You increase the temperature, then it will generate hydrogen. But there is again a lot of research going on. You can say how to cool it. There is a coolant because once you start increasing the temperature, automatically it will, the pressure will increase. So how to cool it? Okay, all about IP generation. From the morning, you have not heard anything about IP protection, but all the works involves IP protection. First, we are protecting the IP. We are doing the patent. So till now, I am not presenting any kind of design because we are in the process of filing a patent. So from this work, I will be concluding my talk. So I hope this is within the time. Thank you very much. This is my group that I have PhD students, project staff, and my science colleagues, scientists. So thank you so much for the opportunity.
Thank you for staying on time. Okay,
So next question.
this talk is open for questions. Anyone? Okay, for the indoor lighting, what is the efficiency of conversion?
We are hunting for more than 30%. This is the target. Till now we have achieved 28, 26 to 28%.
Wow.
So we are going beyond 30%.
Very good.
Yeah. Thank you.
All right, so it's my pleasure now to
Yeah. Thank you
hand
so
you
much.
this as a token of our appreciation. Maybe you want to look at the camera.
Yeah. Thank you.
Thank you once again. So now we move on to the student presentation. Each one is 10 minutes. So the first one, is Devendra Kumar Singh, Rajkumar Verma, and Rajkumar Verma. Is he in the audience? Oh, so okay, through Zoom. Okay, you can represent us offline. Okay?
Okay, okay, sir.
Okay. The floor is all yours.
Okay. My presentation is visible?
Yes.
Sir, my presentation is visible?
Yes.
Yes, sir.
Okay, okay. Good evening to all of you. Today I am going to present my paper. It is actually a review study on the enhanced ultra high molecular weight polyethylene the role of hybrid nanofilters in biomedical applications. The work is collaborative work between Professor Rajesh Kumar Verma and myself, Devendra Kumar Singh. These are the outlines of my presentation. First of all, there is the introduction, then ultra high molecular weight polyethylene reinforced with carbon-based nanofillers. Then I will discuss about the UHMWP reinforced with metallic nanofillers. Then UHMWP reinforced with hybrid nanofiller, which we are actually working nowadays. And after that, the future scope and recommendations, conclusion and analysis. As we know that with the advancement in biomedical sector, nowadays people are and researchers are working most commonly on the polymeric biomaterials because they can be easily tailored, can be easily modified. It is also cost effective. Biocompatibility can also be improved easily with the doping with different types of fillers or antibiotics and other medicinal components within the matrix, polymer matrix. So the concentration of the new concentration, or we can say that, so the new era of the development of biomedical implant is mainly concentrated around the polymeric biomaterials. The supplement with the also with the development of graphene and its derivative, different types of carbon-based nanofillers are already used by different eminent scholars earlier, and still the hunt for the search of new and advanced biomaterials is going on, and different researchers and we can also see that in many recent publications, the people are working for the various types of carbon-based nanofiller reinforced with different polymeric implants, polymeric materials to develop a biomaterial implants or different biomedical devices which can be used for the well-being of our society. So our work is concentrated on UHWP polymer matrix, and we are using the reinforcement method for the development of hybrid polymer implants. And the biomaterial which we are working is concentrated on the use of hybrid nanomaterials which consist of carbon-based nanomaterials nanomaterials and metallic nanofillers. These are the applications of polymeric biomaterials which are used in our human body. You can see that from this figure that there is a large number of or enormous use of polymeric materials within our human body, such as it can be used in skull membrane, jaw implants, and knee implants, hip implants, acetabular cuff liners, and many more. These are the various uses of UHMWP implants, and people have already used this material for the development of different types of implants which are used in our human body. And mainly this material is used for acetabular cuff liner of new implant and meniscus of the knee joint. And this material finds its application for the articulating material development in the biomedical field. This is the economy of hip joint. We can easily see from these figures that a hip joint is consist of a collective joint which consists of a femur connected with the femur head, and it is connected to the acetabular cuff liner, and which fits into the hip socket. So the material which we are developing or which we are going to develop will be used in the acetabular cuff liner, which is placed in the hip socket so that it can reduce the wear and tear of the joint. As we all know that in our day-to-day life, we are going through various types of physical activities, also the long sitting hours of our daily routine and sports activity. Also, there are some situations by which the person is also diseased by birth. So there is a need of development of such type of biomaterial which can be used for various articulating surface within our human body, so that with the minimum number of surgery or minimum number of applications, the person can live a good and healthy life. These are the parts of my introduction, and from this I want to say that apart from the enhanced properties of the UHMWP, the UHMWP still lacks the certain properties, and people are still working for the development of higher strength and wear resistance material, and for this UHMWP is incorporated with different types of nanofillers because of their incorporated properties, and an optimal combinations of material performance and cost may be achieved by reinforcing thermoplastic materials with the different carbon-based nanomaterials and ceramic fillers as well as metallic fillers. Already used carbon-based nanofillers are such as CNTs, MWCNT, SWCNTs, and graphene oxide, reduced graphene oxide. And in ceramic field, there are the ammonia, zirconia, and hydroxyapatite, and so on. Also, in the metallic reinforcement, people have used gold, silver, zinc, and so on. These are the literature surveys of the UHMWP reinforced with carbon-based nanofillers. The addition of carbon-based fillers to the ultra-high molecular weight polyethylene matrix improves the mechanical and radiological characteristics of the biomedical implants. One of the researchers has used reduced graphene oxide and graphite for the reinforcement of UHMWP to increase its property, and he has found that an enormous increase in the mechanical as well as the radiological characteristics has been seen. Addition of 1 weight percentage of RGO resulted in 2.8 in percentage increase in the micro hardness and improved crystallization degree of 46.96%. A study conducted by Nair investigated that when MWCNT, talc, and graphite is incorporated within the UHMWP polymer matrix, and it has been seen that the mechanical as well as radiological characteristics have improved. With the addition of 15% of talc, it has been seen that there is a decrease in the friction and the wear characteristics of the developed biomaterials. Also, it has been seen that with the incorporation of multi-one carbon nanotube, the radiological property has improved a lot. and because of the layer by layer form of the carbon nanomaterials, it shows a lubricating property which is essential for the articulating surface which we are going to develop. These are the tabulated form of recent literature which has been studied by us, and also recently these research has been published in various good journals, SCI and ESCI journals, and we can see that the people are working with the carbon nanomaterials with the incorporation with different polymer matrix and such as UHMWP, UHMWP and PLA and PMMA and so on. And it can be seen that with the incorporation of these carbon-based nanoparticles, the improvement in the traversal characteristics, thermal properties, and mechanical properties has been observed. And these materials have found its applications in various biomedical settings such as in plants. Also, not within the biomedical settings, these materials also find applications such as in food industry. There are different conveyor systems which need such a type of material which has higher wear resistance. Also, they are biocompatible, not as toxic. So, this field is very good and is noble for the development of new materials, and it can be worked out. These are the reinforced. These are the latest surveys of the metallic-based nanofillers reinforced with UHMWP. And recently, a study published shows that the magnetic nanoparticles, when filled with the UHMWP filled with the magnetic nanoparticles, it has been seen that with the incorporation of 1% of the magnetic nanoparticles, the mechanical characteristics such as hardness and wear resistance has improved. Also, the biocompatibility has not shown any harsh result, and this material with the incorporation of iron-based magnetic nanoparticles can be used for biomedical settings. Also, in metallic nanofillers, there are different types of nanofillers such as gold nanoparticles, silver nanoparticles, zinc nanoparticles, and so on. As we know that gold is essentially used in biomedical settings, but because of its cost considerations, we are shifting towards less costly nanomaterials or less costly materials. But because of the good properties of electrical and optical properties of the gold nanoparticles, it is also be used in the biomedical settings, and it can be. And these are the other silver-based nanoparticles reinforcement with the other type of polymers. These are the tabulated view of the silver-based nanoparticles with different polymer matrix, and it can be seen that this type of materials can find application in plants and medical applications. And because of its antibacterial and thermal property biocompatibility, silver-based nanofillers can be used in polymer matrix for its advancement. And these are the resistance of hybrid nanofillers. As we know that a single nanofiller cannot fulfill all its requirements for the biomedical applications, as biomaterial differs from person to person and environment to environment. So the new trend for the development of biomaterials is the incorporation of one or two types of nanomaterials having its own properties so that it can improve the biomaterials. So we have seen that researchers have used different types of nanomaterials such as use a combination such as graphene, MWC, DCND, hydroxyapatite has been used in combination with different types of another nanomaterials for the development of a good hybrid and more advanced material. Yes, sir.
I have to cut you off here because we have two more talks. Thank you so much. And we don't have time for any questions. Thank you for participating. So let's go on to the next one. So the next speaker, thank you. The next speaker is Arvind Pathak.
यार डेस्क पे भी
So please try to stay on time. 9 minutes, nine minutes or so. Don't give too much introduction. Tell me about your work.
Okay, I'm not this partner. One of my students was also involved in this study, and Professor Dr. Vinay Kumar Sir was my supervisor during my research work. Okay, I'm working as an assistant professor in Department of Chemistry, it's on multiple campus in University. The topic is enhancement of the physico-chemical properties of lead clay-based geopolymer composite through nanosilica incorporation. Actually, geopolymer has been applied for transformation of waste materials such as slag, fly ash, as well as the clay materials such as the metakaolin, kaolin, red clay, as well as red mud, etc. We found that in this study, we have introduced the nanosilica for the enhancement of physico-mechanical properties of the geopolymer. So these structures, the ancient structures, as well as the recent application of geopolymer that have been used in the structural for the structural purpose, and reducing the carbon dioxide emission. The replacement of it's a complete replacement of cements. These are made up of geopolymer. The geopolymer, in fact, this a chemical reaction between the solid aluminum silicate oxides and alkaline activated solution at an ambient or slightly elevated temperatures, yielding an amorphous to semi-crystalline polymeric structures. It comprises several units. There is polysiloxo, polysilate, polystyrate siloxo, and so on. This is the mechanism of geopolymerization. It is dissolution. It involves dissolution, gelation, as well as hardening by formation of 3D network. This is the original aluminum silicate grain. Upon the treatment with alkaline activation, there is different stages of reaction that is shown from from left to right. In fact, this is the research gap that is an attempt to replace the cements, at least to some extent. And in this study, we have used the red clay material for the construction to fulfill the construction demand. These are the main objective of the study. That is the effect of incorporating nanosilica on the geopolymerization of red clay through the several specific objectives. Red clay, especially red clay that is used and found in the different places in Nepal as well as in India. This is the synthesis process of nanosilica extracted from rice husk ash. And from rice husk ash, about 18% of nanosilica have been extracted through these processes. And that is used in the incorporation to prepare geopolymer. This is the conceptual framework. The nanosilica, in addition with the calcined white clay as well as red clay, it transforms in alkaline medium and occurs through the several steps, finally obtained the hardened cementitious material, which is under the studied for their structural properties as well as the mechanical properties. These are the experimental steps. Several parameters were chosen for optimization process. This is the chemical composition, mainly silicon, aluminum, as well as iron is involved in the process. The XRD pattern of the product, the raw material, red clay, when added with the calcined white clay as well as nanosilica, this is the addition with the 10% of calcined white clay, and further, when 5% of nanosilica was added. Mainly in these, there is a silica that in the form of quartz was observed. By FTIR analysis, this is the main reason from 900 to 1200. This is the SiO-Si band, 1006, 108, 695, due to the SiO-Si. Here there is a shift of this band towards the right side. This indicates the geopolymerization. It is incorporation of aluminium into the network, as well as this broad band that indicates the reaction. Here we can see here again it shifts to left, and this again due to the silica incorporation. When this is for the 5% silica when added, we have obtained this type of banded which shifts from right to left. That can be seen here clearly. When calcined white clay was varied, an optimum compressive strength at 10% of calcined white clay was added, that is, it was obtained. When nanosilica was added, after the addition of calcined white clay, 5% nanosilica, up to 5% nanosilica, the compressive strength increases and then decreases due to the agglomeration as well as the precipitation due to the excess silica, unreactive silica. Effect of curing time. During the curing time, if when the temperature increases, there is an increase in compressive strength, and it was varied up to 80 degrees centigrade. The percentage at about 65 degrees centigrade, it was found that there is a maximum changes, maximum enhancement in the strain. Therefore, for further study, temperature of 65% was selected. This is the effect of curing time. That is, strength increases with the time. It was the test for thermal stability. When the product after 28 days, when treated with a 300 degrees centigrade and 400 degrees centigrade, there is an increase in compressive strength was observed. This was the physical properties. And apparent porosity, in fact, less than 17, that can be used for the application with a good strength of 20, more than 20 MPa.
Please wrap up your talk. Yeah, good.
Okay, addition of 10% of calcium white clay to the local red clay that increases the compressive strength. Similarly, 5% of nanosilica, there is an increase in compressive strength of about 25.6%. However, this is the optimum value of nanosilica addition. Curing temperature of 65% was found to be optimum. Further increase was not significantly increases in compressive strength, and also by the addition of 2% of lime that also enhanced the compressive strength by 65%. And the geopolymer composite of RWC10 and RNS5 when heated at 400 degrees centigrade for 1 hour, that it was found to increase in about 181.9 and 164.9% respectively. Water absorption value as well as the of the geopolymer composite that reduces with the addition of nanosilver, and thus produced geopolymer composite is a good fire resistant and is suitable for building applications.
That's fine, thank you. I think that's fine, we can read this. Thank you so much.
Thank you.
So let's have a last minute. And in the interest of time, we will not have any questions. We'll go to the last stop for the day. We are already, the cultural program starts at 6:30. We are at 6:30 now. So please stay on time. Okay. So what's your name? Sushmita. Okay. Thank you. Thank you.
So very good evening, one and all. I'll not be taking very much time. So my topic is exploring graphene for detecting radioactive materials in water, a DFT study. This basically we have tried to explore the radioactive elements in the water using a density function theory analysis and non-equilibrium Green's function. And so these are the important points I am going to cover during the presentation, including the introduction, motivation behind the research, literature review, some resultant analysis. So the current study basically involves the water contamination. Though there are so many type of water contaminations like heavy metals, then some kind of biomolecules, then atoms, but there is also some one important thing that is radioactive elements. So there is lots of radioactive research and the industrial exploration has been done. So many impurities are present in the water due to radioactive elements. So it is also important to analyze the radioactive element and filter them out as it poses the human health risk. So we have tried here using the graphene sheet. Why we have used graphene? Because it has a very large surface area, it is good biocompatible, it is hydrophobic in nature, so it does not react with water, but so can use for sensing the impurities. So and also it is durable, low cost, and has some high thermal and electrical conductivity. So motivation behind using this is because it has a very high surface area. It is occasionally being used for sensing of many gas molecules and other pollutants. So also we have also there are some literature review based upon the water pollutant, where multiple water pollutants has been sensed using the graphene sheet because of the high surface area. So that is the reason we have selected this graphene as and also try to analyze. The computational methodology includes the density function theory and non-equilibrium Green's function using the quantum etiquette rule. The density function, using density function theory, we have optimized the structure having a graphene sheet with water molecule, and as well as we have kept the different contaminants of the radioactive elements, and we try to optimize them. Then we try to check the electronic properties as well as the transport properties, and we found some changes. So as an exchange correlation function, we have used generalized gradient approximation function using the revised Purdy as an model. And there are some other parameters like double theta, double polarized basis set has been used. The different K points mesh has been checked before going for the optimization. So these are the main radioactive contaminants we have focused. So first is radium. Radium is the source is uranium decay in the rocks. So health impact consists the bone cancer and leukemia and also other health risks. So it is generally solid in the form and contains the radii of 0.215. The radon is similarly source is decay of radium and aquifers. Similarly, francium and thorium are also the radioactive elements which causes health risk and can be a contaminant in the water. So this is the basic structure we have taken. First is the graphene sheet. You can see the graphene sheet. This is a graphene sheet 2D structure, and then we have optimized the structure of the graphene sheet initially. Then we found the water molecule. Water molecule has been optimized here. Then we took a radioactive element, atom, single atom. Then we try to optimize the structure and we check for the properties, the change in the properties. So initially, when we checked for with the water molecule, what we have observed was the structure, the band structure was same as well as the density of state. There is no change because it is not reacting with the water. Then we checked for the when we kept the radioactive elements near the water, like near the graphene sheet, we found there is some significant change in the band structure. As we can see, the band structure, the direct cone is moving towards the valency band, so it is showing the p-type phenomenon. And then, as well as the loss is also changing. We can see the states are present, and there is a change. So similar found in the band structure we have added. So not for the radon. Radon there is no effect of radon as it is an open gas. So we found no change in the band structure as well as in the loss. But then we found the change similar to the previous radium. In the francium, when we introduced francium, there was a change in the band gap. There was some indirect band gap present when we just kept the molecule of like atom of the francium near the graphene sheet. Similarly, we found the change in the density of states also. Though the energy states has been the electron states has been increased near the Fermi level, but the band gap was present in this case. So similar to this, then we have the thorium atom. Thorium atom also, when we kept near the surface of the graphene sheet, we found the band gap has been introduced. It's a direct band gap here, and then also the states has been changed. The loss has been significantly changed. So then we obtained the absorption energy. We have done the absorption energy analysis using the total energy of the system minus the total energy of the adsorbent and the sheet. So what we found was there was enough absorption present in the case of radium, francium, and thorium, but there was no change, much significant change in the radon because it was not sensing it. And also there was a significant, this value is not there, Mulligan charge analysis. The charge transfer was also significant in all the three cases other than the radon. Then we did the transport analysis using the NEGF. We have optimized the 1D structure of the graphene sheet. We extended towards the left electrode and the right electrode and found the central region. And in the central region, first we kept the water molecule, then we kept the radioactive elements one by one, and then we found the change in the current voltage analysis. So there was not much significant, but we found some change in the IV curve. So this is the change, not much change in the radon. So similarly for the francium and the thorium, we found some change. The current was decreasing in all the cases actually, whenever we are putting it near the surface of the graphene sheet. So as an outcome, we observed that it was able to sense, the graphene sheet was able to sense the radioactive elements, which was radium, thorium, and francium, but not sensing the radon. So in conclusion, we can say that it is a potential, the graphene sheet is a potential candidate for sensing the water impurities or the pollutants, either in the heavy metals or the radioactive elements. So we can find its suitability and reliability, and can do some further experimental studies on this. So, thank you.
Very good. I think so. We will conclude the session because we are out of time. Thank you, Vanessa. So let's thank all the speakers of this session.
So everyone, you all have around 15-20 minutes to within 15-20 minutes you all have to reach to auditorium for cultural program.
And thank you, respected sir.
Thank you, respected sir.
Thank you so much, sir. Thank you very much, sir.
Auditorium is there where morning session was.
Where the inaugural.
Yeah, inaugural ceremony was there.
I asked Prakash that